Okay, good evening, everybody. And welcome to another session of organic chemistry. In today's session, we are going to finish up on chapter 8, which deals with the chemistry of alkenes. Specifically, we are going to discuss the various reactions of alkenes. But before we do that, a couple of announcements. Reminder that the next class exam is scheduled for next Tuesday, that is October 22nd. And also, we are going to have an online review session on Sunday, October 20 at 8 p.m. That is Sunday, October 20 at 8 p.m. online review session. I will send you the link to that session as a reminder. Okay, so let us go ahead and do that. Those are problem sets that you guys have just done in your quiz. Okay, Ashanti, can you go ahead and read this for us? Okay, thank you. Very good. Okay, so in this question here, the question is, in the acid catalyzed hydration of 3-methyl-3-hexene, what type of carbocation intermediate is formed? This question is testing your knowledge of nomenclature. This also testing your knowledge of reaction mechanism as it relates to the electrophilic addition reactions to alkenes. You must know that the first step in that reaction mechanism is the formation of a carbocation as a result of addition of a proton. Okay, so what do we have here? I say hydration. Hydration means you are adding the elements of water, which is hydrogen and OH, across the carbon-carbon double bond. So, for example, if you have this, say we have this molecule here, and for hydration, you're essentially going to add water, but however, water by itself would not add to a carbon-carbon double bond, so we do need to have an acid as a catalyst. So very often we have H2SO4, which is sulfuric acid. And then also, sometimes we refer to this combination here as dilute acid. So sometimes we may simply just tell you dilute acid. That would be a combination of water, a solution of mineral acid, sulfuric acid in this case, in water, or sometimes phosphoric acid, or sometimes nitric acid. Okay. So this reaction here will give us addition of element of water, which is hydrogen and OH, across the carbon-carbon double bond. And this will be a Markovnikov type addition, okay, which means that the hydrogen comes here, and the hydroxide will go here. Okay, so we expect to get this. However, in this question, all they wanted to give is the intermediate carbocation. Okay, so let us see what is going to happen here. Okay, you have 3-methyl-3-hexene. So we need to know the structure of 3-methyl-3-hexene. So that would be this here. Okay, so that is 3-methyl-3-hexene, position 1, 2, 3, 4, 5, and 6, and the methyl in the 3 position right here. Okay, so what is the first thing that is going to happen? You know that this here, water in the presence of sulfuric acid gives you the hydronium ion. Okay, this is your hydronium ion here. And you may want to think of the hydronium ion as this here.
Mm-hmm.
Okay? So now, the first thing that happens, you have the pi electron here. Keep in mind, this is a mechanical addition. So where do you expect the hydrogen to go? Let me number this. 1, 2, 3, 4, 5, and 6. Which carbon do you expect the hydrogen to go? Carbon number 4. So this is a mechanical addition. Very good. Okay. So the pi electron, the 2 electron moves here to grab this hydrogen here. And in so doing, we are going to break the hydrogen-oxygen bond. So we form this. Okay? So at this point, the carbocation is on this carbon right here. As you can see here, this hydrogen comes to this carbon here, carbon number 4. And that is right here. And now you have the carbocation. So what is the answer to this question? Okay, what is it? A, which is, this carbocation is a tertiary carbocation. Very good. Okay, that's the question that you are supposed to answer. Okay, so the answer here is A, tertiary carbocation. Okay, so let us go to 2. Jero, can you read this for us?
For the first reaction in the first phase.
Okay, thank you. Okay, for the following reactions, you need which reagent? Okay, the question I ask for you here is you look at this starting material here, and you look at the products. So what kind of reaction is, what are we doing here? Adding water, exactly. So this is an hydration reaction. This is hydration reaction. Okay? Okay, of all these reagents that we have given you, which will be the reagent we need to do this? Keep in mind, this is a mechanical addition. Because the hydrogen comes to this carbon right here, and of course, you see the hydroxide goes here. Okay, so this is another mechanical addition. Okay, so of all these reagents we're giving you here, which one will do that? Which one will add hydrogen and OH across a carbon-carbon double bond in a mechanical fashion? B, very good. B is correct. Remember I told you last time on Tuesday that you simply need to know what those reagents do. You need to know what the reagents do. So in this case, this is what you have here. Anytime you say mercury acetate, of course, in this case, in water, step 1, and you follow that up with sodium borohydride. This reagent here, what it does is to add hydrogen and OH across a carbon-carbon double bond. You need to be able to say that in your own words. Each one of these chemical reactions here is a language. So don't just write them, you need to say them in your own words. What is this doing? Okay? Not at this point we are not asking you how is it doing it. That is mechanism. Okay, what we're asking you now, what is this doing? What is it doing? It's adding hydrogen and OH across the carbon-carbon double bond in a mechanical fashion. Okay? Okay. So the answer here is B. Supposing we wanted to use C. Supposing we wanted to use C, what product will you get? What does C do? Yes. I'll say it in your own language. Be very explicit. What does it do? It adds, no, what does it do to a carbon-carbon double bond? It adds what? No, okay, go ahead. But what is it going to do though? Okay. More hydrogen. Okay. In other words, this reagent here, what does it do? It will add hydrogen and OH across a carbon-carbon double bond in an anti-mechanical fashion. You need to be able to say that. So only when you say that, then you understand what is going on. Okay? So this reagent here, C, hydroboration oxidation, what it does is to add hydrogen and OH across a carbon-carbon double bond in an anti-mechanical fashion. In other words, the hydrogen goes to the carbon that contains more hydrogen. The hydrogen goes to the carbon that contains less hydrogen in this case, and the OH goes to the carbon that contains more hydrogen, which is anti-mechanical. Okay. So anyway, in this particular instance, the answer here is B, because this is a mechanical addition of water across the carbon-carbon double bond. Yeah, Hutchinson, you read this first.
Supply the missing starting material or product for the following reaction. No mechanism required.
Okay, thank you. Okay, in this question here, it says supply the missing starting material or product for the following reactions. No mechanism required. Okay? Okay, so what do we have here? We have hydrogen chloride, and then we have this product here. So what type of reaction is this? Do you think this is? What does hydrogen chloride do? Will add to carbon-carbon double bond. One of the reactions of hydrogen chloride is to add to carbon-carbon double bond. Okay? So in this case, we see this product here. And of course, this reaction is also a mechanical type reaction. Okay, so we see this product here. The chlorine is here. So what are how many possibilities do you think we are going to have here in terms of the starting material? 2, right? Exactly. 2 possibilities. Let me write this here. So we could have this. That is a possibility. If you add HCl to this hydrogen goes to here. Okay? Right? Is that what we have? No, I'm sorry. The hydrogen could go to here, right? Okay, this hydrogen could go to here, and now the chlorine goes to here. Okay, another possibility would be is this here, in which case the hydrogen goes here and the chlorine goes here. Each one of these possibilities here will give you this product. Yes.
First one, why would the hydrogen go to that particular one if both of them only have one hydrogen?
Yes, very good question. In other words, what you are asking here, why not let us number this? 1, 2, 3, 4, 5. Okay. Why doesn't the hydrogen go to carbon number 2? Is that your question? Okay, but the product we gave you is this. You have to look at the product. If this is the product, then the hydrogen cannot go to carbon number 2. Okay, so you have to look at the product we gave you in order to give you the possible solution to that problem. Yes.
What she was trying to ask is why, according to Marconico's rule, isn't it just based on the number of hydrogens on the carbon?
Yes.
That's where it goes, but both of the carbons in the double bond have just one hydrogen.
Well, that's the same question she just asked.
Right, that's what
I said, but the question, the answer to that question is, look at the product we gave you. This is what we want you to explain. This product here, the chlorine is on the 2 position. Okay? So therefore, you got to give an answer that is consistent with the product that we gave you. Okay? Okay. Okay, about this one here. About this one here. Okay, let us number this. Let us call this carbon number 1 and carbon number 2. Okay? Another electrophilic addition reaction. Where does the hydrogen go? Carbon number 1, exactly. So therefore, because this also follows Marconico's rule. Okay, keep in mind there was an hydrogen here initially, so we have so once you know what those reagents do, these questions are really very simple. Okay? Yes.
Do we, like, when we do the notes and stuff, you don't write the hydrogen, do we have to write the hydrogen and put bromine where it's supposed to?
Oh, no, you don't. No, the reason I do that so that you know that the hydrogen was already there. Okay. Okay, let us see here the last one. Okay, Erin, can you read this for us?
The reaction of E220 with chlorine water. Write the product briefly, comment, and explain the optical activity of the reaction process.
Okay, thank you. Okay, so for this reaction, for the reaction of E2-pentene with chlorine water. This is chlorine water here. Write the products and briefly comment and explain the optical activity of the reaction mixture. Okay, so this reaction here requires that you have some knowledge of course, what the chlorine water is supposed to be doing and how it does it. Okay? So a little bit of mechanism is required here. Okay, so what does this chlorine water do? What does it do to a carbon-carbon double bond? Anybody can, in your own language, in your own words, what does it do? Make it as simple as possible. What does chlorine water do? Yes, go ahead. Oh, very good. In other words, chlorine water, what it does is to add chlorine and hydroxide across the carbon-carbon double bond in a trans addition fashion. In other words, the chlorine and the OH will be trans to each other in the molecule. Okay, so let us take a look at this. E2-pentene. Now, the way you approach this, since I've not given you the mechanism for this type of reaction, this is what to do. Okay, of course, you write out the alkene, the structure of the alkene. In this case, we say E2-pentene. Okay, this is the E isomer, stereoisomer. And then, since we know that we are going to add chlorine and hydroxide across this carbon-carbon double bond. So imagine that the chlorine comes here, adds to this carbon here. Okay, when it does that, this sp2 carbon will become an sp3 carbon. In other words, it is going to push down this methyl and this chlorine. The stereochemistry will be this methyl and this chlorine will be pushed down by the chlorine. So what do we have? So chlorine comes here, and the methyl pushed down, going away from you, and the hydrogen also pushed down, going away from you. Okay, when it does that, when the chlorine comes here, since this is trans addition reagent, chlorine coming here, what that tells you, the hydroxide will come from the opposite side on this carbon here. So therefore, the hydroxide is here. Okay, also pushing the hydrogen and this ethyl off. That would be one product. Yes.
Why is hydroxide on the right side? Can chlorine and hydroxide switch?
Yes. Yes, you could start with hydroxide. Doesn't really matter. Okay. Okay. Now the other product would be this chlorine, because if you look at this, this is what you have here. If chlorine comes from here, there is nothing stopping the chlorine from coming from the bottom. Okay? Okay, so now we want to show the chlorine coming from the bottom. Now that we're coming from here, the first chlorine comes from here. The other possibility is coming from the bottom. Okay? Then we have this. Chlorine coming from the bottom, and then pushes the methyl and the hydrogen off. And then this here. So if the chlorine comes from the bottom, that means the hydroxide will come from where? From the top, because they must be opposite. Okay? Okay, those will be the two products. And if you determine the absolute configuration of this here, you will find that these two compounds here, if you say this is compound A and this is compound B, they will be enantiomers. They will be enantiomers. So I will leave that for you to do when you get home. Yes. Yes, you got to draw the two products. Okay, and then since they will be enantiomers, this reaction mixture here will be optically what? Optically inactive. Very good. So this is what we call a racemic mixture. Because you are going to form equal amount of compound A and compound B. Okay. Yes. Sir. Is that a question? Okay. Okay. So at this point, let us go to today's discussion. Yes.
If this is the molecule itself, and if it was these two continuous related, like how are that different from those three?
Which one?
If it was these two continuous.
If the B.
If it was these two types.
Oh, yes. Yes, it will be different, yes. If it is Z, yeah, very good question. In other words, the question is, supposing we were starting with the Z isomer, this is the E isomer. If you start with the Z isomer, then you are going to get different set of products. Because don't forget, in that case, this methyl and this here, they will be on the same side of the carbon-carbon double bond. Okay, so let us go to today's discussion. Okay. Okay, when we left on on Tuesday, we were discussing the reactions of alkene. So what I want to do, I'm going to follow in that sequence of activities. So I believe I gave you reaction number 4 before we left, right? So let me now start with number 5. Okay. Number 5 is what we call oxidative cleavage. In this case, I'm going to write it down for you. In this case, for the oxidative cleavage of alkenes, using ozone, this molecule here, ozone, and after the ozone reaction, you follow that up with zinc in some kind of acid, dilute acid, or sometimes we use acetic acid. Sometimes we use acetic acid, which is this here. Okay? Now if you do that, what does this reagent do? It will cleave the carbon-carbon double bond so that each carbon of the carbon-carbon double bond becomes a carbonyl carbon. Okay? So now this becomes a carbonyl carbon, in this case of a ketone. This also becomes, this other carbon here becomes a carbonyl carbon of another ketone. See? So this reagent, what it does is to cleave the carbon-carbon double bond. Okay, so let us now give you a series of reactions. Okay, I say 5. Oxidative, cleavage of carbon-carbon double bond with ozone followed by dilute acid, to give ketones or aldehydes. And we generally refer to this reaction as ozonolysis. For example, if I have this, okay, and then I have ozone, I do ozonolysis on this. Step 1, it's a two-step reaction. Then step 2, step 1 is ozone, step 2, zinc in some dilute acid. What do? We are going to cleave this carbon-carbon double bond, and then we form this. Plus we form this. Now, supposing we start with this here. Supposing we start with this here. Okay. We cleave this carbon-carbon double bond. This ozonolysis. Ozone followed by zinc. What do you think we are going to get? You get one molecule, one compound, instead of two compounds, in which you have two carbonyl groups in the same compound, right? So now we are going to get this. You get that? Keep in mind what this reagent does is to cleave the carbon-carbon double bond such that you now have two carbonyl compounds, two carbonyl carbons. Now, so far the example that I've given you are examples in which you get ketones. Supposing we have this. Whenever you have an hydrogen attached to any of the carbon-carbon double bond, that carbon becomes a carbonyl of an aldehyde. So we cleave this here. We cleave this right here. This carbon here becomes the carbonyl of an aldehyde, and this carbon becomes the carbonyl of a ketone. So this part of the molecule here, this is a ketone. And this part of the molecule here is an aldehyde. Okay? So what you get depends on whether an hydrogen is attached to any of the carbon-carbon double bond. If no hydrogen is attached to it, then they become carbonyl of ketones. Supposing we have this. Supposing we have that. How many products are we going to get? How many? Okay, we are going to cleave this, right? We cleave this right here. So how many products are we going to get? 2. Okay. Okay, would they be ketones or aldehyde? One will be a ketone, the other will be an aldehyde. The aldehyde will be on this carbon, and the ketone will be on this carbon. Follow that. Okay, so the product is plus this is your ketone, and this is your aldehyde. Okay, so that is reaction number 5. Go to number 6. So, go back. Okay, number 6. Oxidative cleavage using potassium permanganate, which is this here, to give ketones or carboxylic acid. If, for example, I have this here, this carbon here, let me have a, let's put an ethyl group, and this carbon has an hydrogen atom. What is going to happen when you use this reagent here, which is potassium permanganate? Generally, we use this in acid medium. Now, if we do not use it in acid medium by mixed together, you could also do this, potassium permanganate in basic medium. Then this will be step 1, and this will be step 2. You then add hydronium ion at step 2. So you could use either this here or this here. If you do that, what you will get is to cleave. You will cleave the carbon-carbon double bond. That is why we call this oxidative cleavage. You will cleave the carbon-carbon double bond such that the carbon that is attached to hydrogen becomes the carbonyl of a carboxylic acid, and the carbon that is attached to no hydrogen becomes the carbonyl of a ketone. So therefore you have this. Okay, if you see here, this is the carboxylic acid right here, in the same molecule. And here, this is the ketone, all in the same molecule, because we started with a ring system. Yes. Yeah, becomes the carbonyl of a carboxylic acid. Just a minute, let me see. This is carboxylic acid right here. Okay, because this carbon here is attached to hydrogen. So that carbon is the one that becomes this carbon. This other carbon here becomes the carbonyl of a ketone. Okay? Just as in ozonolysis. Okay, you follow that? Okay. Now let's give you a couple more examples before we leave that. Supposing I have this. Potassium permanganate in dilute acid. Okay, how many products are we going to get? And will they be carboxylic acid or ketones? How many products? Two, exactly, two products. Will they be ketones or carboxylic acid? Carboxylic acid, exactly. You are going to cleave right here. So you get this carbon here becomes the carbonyl, carbon of a carbonyl of a carboxylic acid. And this other carbon also becomes a carboxy group. Which is this here. However, if both of the carbon do not contain hydrogen, in this case, supposing we have this, how many products do you expect here? In this case, we have a symmetrical molecule, right? We have a symmetrical molecule. If you click right here, right? This becomes, what kind of compound are we going to form? Ketone. This ketone that we form on this side will be the same as ketone on this side, because we have a symmetrical molecule. So this, therefore, this is the product we are going to get. So we are going to get two molecules of that. Why what? The two hydrogen? Where are they? Because this, anytime you have a carbon that is not attached to hydrogen, you get a ketone. Okay? Now, supposing you have what we call a terminal alkene, supposing you have a terminal alkene, meaning that the carbon-carbon double bond is at the end of the chain. You clip this here, this carbon becomes the carbon of a carbonyl of a carboxyl group. This here, the end carbon becomes carbon dioxide. I see you guys are laughing. Okay. Okay. And carbon dioxide. This carbon here, the terminal carbon, this here becomes the carbon of the carbon dioxide. Okay. So is that number 6?
So whenever the double bond is broken for the last, I guess, 2 carbons, selected for me, carbon dioxide.
Yes, yes. The end carbon, okay, becomes carbon dioxide. For example, if you have this, supposing you have this, okay, and potassium permanganate, okay, you are going to clip this right here. This carbon here becomes the carbonyl of a ketone in this case, because there is no hydrogen attached to it, and this carbon becomes carbon dioxide. So you get this. Yes. Okay. Was that number 6 or 7? 6. Okay, let us go to number 7, reaction number 7. Oh, go back. Say that again. This here? Yeah, it's part of the product. This carbon here becomes carbon dioxide because it's at the end of the chain. Okay?
What if there was more than one? What if there was more than one carbon? Like what if it was like CH2?
But that's not the end of the chain. That would be an internal alkene, so that will give you the regular carboxylic acid. In other words, if you have here CH3 here, then that will give you your regular carboxylic acid. Okay. That's 7, number 7, right? Is that right?
Yeah.
Okay. Okay, let us say addition of oxygen. Using M-chloro-benzoic acid to give epoxide. M-chloroperbenzoic acid to give epoxide. Okay, supposing we have this. M-chloro addition of oxygen using M-chloroperbenzoic acid to give epoxide. Okay. Supposing we have this. We use this here, what we call M-chloroperbenzoic acid. We generally abbreviate the M-chloroperbenzoic acid as MCPBA. So if you don't want to write this structure here, just write MCPBA. What it does is to add oxygen across the carbon-carbon double bond to give what we call an epoxide. Use an epoxide. Now we could also form an epoxide using an what we call hydrogen. You got that? Supposing we okay, I would caption this and say another synthesis of epoxide. If we have this, and we have this, we have, for example, chlorine water or bromine water. We know about that already. What does the bromine water give us? What does it give us? What does it do? We add bromine and hydroxyl across the carbon-carbon double bond. You guys need to know what those reagents do. Okay, that is key to actually knowing organic chemistry. You need to know what the reagents do. Okay, so in this case, we are going to add bromine and hydroxide across the carbon-carbon double bond. If we then take this is what we call an hydrogen or bromo, in this case bromohydrin. The general name will be hydrogen because we could also have chlorine, that becomes chlorohydrin. Hydrogen is when you have hydroxide and bromine or chlorine atom on adjacent carbon atoms. In other words, carbon atoms that are next to each other. Okay. Now, if you now take the bromohydrin, take hydroxide, the hydroxide could come in the form of sodium hydroxide or potassium hydroxide. What you get an epoxide. So therefore, we have two ways of making epoxide. We could make epoxide from an alkene, either using M-chloroperbenzoic acid or using a combination of bromine water followed by hydroxide. The way we could write that, you got this? We could simply do this. Say step 1. Well, let's just change where. Okay, let's keep the bromine there. Bromine water or chlorine water. And step 2, sodium hydroxide or potassium hydroxide. And then what you get is your epoxide. Okay, well that's reaction 7. Okay, let us go to 8. Say that again. Yeah, no, this is one way of forming epoxide. Remember, I gave you the M-chloroperbenzoic acid. This is another way of doing it. Okay, in other words, you do the a reaction with bromine water to form the halohydrin, and then you add the sodium hydroxide to the halohydrin. That gives you epoxide. Okay. Okay. Number 8 or 9. Addition of two OH groups across the carbon-carbon double bond to give what we call 1,2 diol by using okay, let's say that again. Okay, one way we could do that if I take an alkene and I take osmium tetroxide, this is a two-part reaction. Osmium tetroxide, it's called osmium. And then I follow that up with osmium, yes, osmium. I follow the osmium tetroxide with sodium hydrogen sulfide. Sodium hydrogen sulfide. What that does, this reagent here, what it does is to add two OH groups across the carbon-carbon double bond. Now you begin to see why I told you to focus on what the reagent will do, because you are going to get so many reagents. Better to know what they do. Okay? Add two OHs across the carbon-carbon double bond, cis to each other. Okay? So this is a cis addition product. So therefore, this reagent here, the osmium tetroxide, is therefore a cis addition reagent. Cis addition reagent. Sometimes you might see in some book, instead of saying cis, they might use the word syn. S-Y-N. Okay, syn addition reagent. It means the same thing. Okay, what is important here is this reagent here, what does it do? What does it do? You add two OHs across the carbon-carbon double bond such that the two OHs will be on the same side of the molecule. In other words, to be cis to each other. Now, supposing you want to add the two OHs trans to each other. You guys are looking. You see, I have plenty of time, don't you? Okay. Supposing we want to add the OHs trans to each other. Nine. Okay, trans addition of two OHs across the carbon-carbon double bond. If you want to do that, what you do, you take an epoxide. You take an epoxide and you add dilute acid, in this case hydronium ion, I call dilute acid here. If you do that, you will open up the epoxide so that you now have the hydroxide will be trans to each other. Okay? Another way you can look at it, say for example, you could simply take suppose you will take step 1, M-chlorobenzoic acid. What would that do? What would that do? Epoxide, okay? And then step 2, we dump in some dilute acid. Okay? That will give you this here. Okay, so should I give you guys a break at this point? Okay, so whatever we do in the exam will be where we stop today. Okay, the rest of chapter 8 we will finish next week. Yes. Huh?
Can we establish that the bottom reaction would make an epoxide, not whatever?
No, the first part, the M-chlorobenzoic acid gives you the epoxide. Then you add this here to give you this. Okay, so let me give you back a lot of your quizzes back to you. And then don't forget, we'll meet on Sunday at 8 p.m. for those of you who have the time to join us. And the exam will will be wherever we stop this chapter. So the rest of the chapter we will finish next week.